Hello and welcome to the Cryosphere Pavilion. I am Gabrielle Kleber. I'm a postdoctoral researcher at the University of Tromsø in Norway. I'm here to present today's session, which is Climate Change Increases Antarctica's Vulnerability to Extreme Events. I will introduce our first speaker, which is Jonathan Willey. He's a postdoctoral researcher at ETH in Zurich.
Hello, everybody. Yes, today I'm here to discuss my research that covers a lot about the impacts on moisture transport events and how they trigger extreme weather events over Antarctica. So first, just some context. Here's Antarctica. Now, when we think of Antarctica, we should always remember that Antarctica is a desert comprised of grounded ice sheets and floating ice shelves. And as any good desert, precipitation annually is very low over a majority of the continent. But as there's very low precipitation, it means that it's very sensitive to extremes in precipitation. As you would see a flood in a desert, you can have a massive snowfall event that's very unusual for the ice sheets and the ice shelves in Antarctica. So I'm going to begin with a little story. We're going to start in West Antarctica, specifically at Waste Divide, which was a camp used for drilling ice cores. And it's quite high in elevation, quite cold as well. And when I was working as a weather observer in 2016 at Waste Divide, we were actually encountering a very extreme weather event that we had no idea was coming at the camp, where it normally is around minus 15, 20 degrees. We had temperatures rise to 0 degrees, and we had these rather unusual, very thick liquid water laden clouds come over the camp, which was actually part of a very broad melt event that was going across all the West Antarctic ice shelf and the West Antarctic ice sheet at the time. And we had places at Bird Camp that was just slightly lower actually exceed the melting point and have melt recorded there. And that, in fact, melt was recorded over a large portion of the West Antarctic ice sheet. And was mostly induced by a sort of a large perturbation in the polar jet stream, which allowed warm, moist air to get into the continent. Now, later on, I went back to look at this event and figure out like what kind of storm actually triggered such a extensive heating over the continent. And I saw this kind of cloud signature, and it looked familiar from something we would see more often in the mid-latitudes we call an atmospheric river. What is an atmospheric river? Because I'll be saying it a lot over the next 15 or so minutes. So basically, this image here is showing the areas of global water vapor around the world. Most of it concentrated around the tropics, as expected. But you see these little fingers extending into the polar regions. That is what we consider the atmospheric river. They actually contain 90% of the total global polar moisture transport, despite being so small, actually. And a bit more meteorological, they're often associated with the extratropical cyclones that happen around the world, but not all the time. But you often find them ahead of a cold front, embedded within the lower part of the atmosphere and what we call the low-level jet. But they're actually essential for causing what we call the explosive cyclogenesis of cyclones, and it can actually have large impacts on the large-scale circulation patterns of the jet stream as well. So, and also, they're also often associated with blocking in the atmosphere. So here's an example of one atmospheric river in California where they happen very often. And you can see this large blocking ridge to redirecting the moisture far into basically the British Columbia and southern Alaska. Now, like I mentioned before, my little desert analogy, this was an example of an atmospheric river hitting the Atacama Desert, a place that normally never sees rain. And this was the result here from an event that happened in March of 2015, causing extensive flooding. Now, we also now know that atmospheric rivers can be linked with heat waves. This is a very good example of what you call a very extreme weather event that happened in June of 2021 in Western North America, where we had excessive temperature values of around the upper 40 degrees Celsius happening in Western North America. And it was far more extreme than any other heat wave that had been observed in any other part of the world up until that point in time. And we actually had the town of Lytton, Canada, set the all-time maximum temperature record for Canada reaching 49.6 degrees Celsius, which shattered the previous record by 4.6 degrees. And then the next day, the town burned down in a wildfire. It was a truly astronomical heat wave that really captured the attention of the global weather community. And research into that event did show that the moisture related to an atmospheric river did contribute thermodynamically to the some additional heating. I won't go into too much detail about that. And then also, there's a bit of a dynamical effect as well, the way the moisture transport can amplify the jet stream, but this is still a bit murky, this area of research. But this event is what we call a black swan event, because black swans are very rare. So that term got kind of co-opted into meteorology and climatology. There's an event that maybe we should have saw coming, but given previous experience, was just never expected. Even in looking at weather models, it's just they're quite off the scale, and they're very hard to predict. That's the problem, and especially in climate models, they're incredibly difficult to find. This paper from Fisher in 2021 kind of shows how global warming makes these events more frequent, because you have sort of had a baseline and a stable climate of where temperature records could happen. But as the mean temperature increases, now you're also increasing the upper threshold of possible extreme temperatures. And that's why it seems like every month you hear something in the news about some new record-shattering event happening someplace in the world. So that doesn't, it's not just limited to the mid-latitudes. We also see these events happening in the polar ice sheets, especially because they're warming even faster than the mid-latitudes. So why does this matter, though, for the polar ice sheets? So quick little background in how the mass balance of Antarctica works. When it comes to most weather phenomenon, we are talking about the surface mass balance, which is just sort of the product of the deposition of snowfall onto the continent. So that's the mass gain. You have sublimation, so that's snow that just gets evaporated directly into gas, sublimated into gas, sorry. And then you have melting, so snow melts, drains into the ocean. That's the surface mass balance. Then you have the discharge term, so that is the ice flowing into the ocean due to more glacial dynamics. And that if you combine the surface mass balance with the discharge, you get the total mass balance of the Antarctic ice sheet. Now, we know Antarctica is losing mass overall, especially being driven by mass loss in Western Antarctica. But the East Antarctica actually shows slight gains in mass. It's been sort of acting as a slight mitigating impact on the total sea level contribution of the Antarctic ice sheet. And we actually see that increasing snowfall during the 20th century is actively contributing to this increasing mitigating factor. But this whole process is still relatively low confidence, even in current IPCC projections. The process is controlling the stability of the ice shelves, and instabilities. We believe they will become more common in the future, but we need more research into this. So this is where my research begins. So first, I will discuss how atmospheric rivers impact surface melting and ice shelf instability across Antarctica. First, we have to identify the atmospheric rivers. So we use an algorithm to do that. And the first result is that the atmospheric rivers, or ARs, as I call them, are actually exceedingly rare. They may happen a few days per year on the coastlines of Antarctica. So, okay, so they're very rare events. What we find is that despite being rare, they're very high impact events. So this diagram here shows, going back now to that first image I showed you of the heat wave of the melt event in Western Antarctica. Here now we can show that it was caused by an atmospheric river, and we now detect it, and we show that like the large liquid water content of the clouds was driving a lot of the radiative heating on the continent, and it actually caused large amounts of melting across a lot of the Ross ice shelf and even higher elevation regions. But then when we compile all the detected atmospheric rivers that happened over the past 40 or so years, we find that the most melt, almost a majority of it, and actually almost all of it in higher elevation regions, could be attributed to the atmospheric rivers in the summertime across West Antarctica. And actually winter on the Antarctic Peninsula, most of the melting could be attributed to atmospheric rivers as well. Now, another component that is keeps, well, ice shelf and ice sheet scientists up at night. It's the collapse of the ice shelves around Antarctica. We already here saw the spectacular collapse of the Larsen B ice shelf in 2002, where this, in a matter of months, this ice shelf completely disintegrated. So in this study here, we looked at how atmospheric rivers actually were related to the instability of the ice shelves. This was a particular example from January 2008. Now the ice shelves are gone by now, but now they've been replaced by what we call landfast ice, which is pretty stable ice. But in this example, we have a large atmospheric river. We can see it on the panel D over there that made landfall in the West Antarctic Peninsula. And just 6 days later, the landfast ice was turned into essentially Swiss cheese and completely disintegrated. And also, we simulated a large amount of runoff and melting that happened just because of this event. And in this study, we kind of created this conceptual model of how these atmospheric rivers can actually lead to the collapse of the ice shelves. Basically, as you have this warm stream of air hit the continent, it rises as it hits the mountains, it releases what we call latent heat that down descends and what occurred called the Föhn wind on the leeward side of the mountain ranges, and that warming air also. So we have the dry clouds causing radiative warming aloft. That leads to warm temperatures over the ice shelf. That causes melt pond formation, which leads to hydrofracturing. At the same time, they're also causing the sea ice to disintegrate off the coast of the ice shelf. That leaves them exposed to ocean swells, which also destabilizes the ice shelves. And in fact, when we looked at the collapse of the Larsen A and the Larsen B ice shelf, they were both preceded by very large atmospheric river activity that kind of, we believe, triggered the final collapse of these ice shelves. Of course, the ice shelves are impacted by ocean components as well that can lead to their slow decline. These events can act as sort of a kicker to increase the rate of destabilization. But also, I'd be amiss if I didn't mention all the snow that atmospheric rivers also cause. So using, again, this algorithm, we find that the atmospheric rivers contribute a lot of decent percentage of snowfall, especially in Eastern Antarctica, the total annual snowfall budget of around 20-30%. When we talked about the heaviest snowfall events, those in the 99th quantile, a majority of those heavy snowfall events could be attributed to atmospheric rivers, and again, particularly in East Antarctica. And in fact, we find that the trends in the atmospheric river are the same as the trends in snowfall around the continent. So you have increasing snowfall in Queen Mon Land, in Joining Mon Land, Queen Elizabeth Land, and decreasing snowfall in Wilkes Land, which matches the trends of the atmospheric rivers. We actually can attribute most of those trends to the frequency of atmospheric rivers, and actually find that, and not shown here, but atmospheric rivers do control even the interannual variability of snowfall across the continent. So now we get to our very own black swan event in Antarctica. So we had this papers published actually just a couple weeks ago. It was a huge collaborative effort from, well, let me go back. Basically studying this one extraordinary heat wave that happened in March 2022 in East Antarctica. So what happened was this event caused massive temperature warming over the East Antarctic ice sheet, and it was very well represented in the global media. Even it was actually regarded as the highest temperature anomaly ever recorded on planet Earth, happening over Antarctica in this case. So this event caught the attention of scientists, around many scientists in the Antarctic community. So 54 of us decided to study all the components of this heat wave event, everything that we listed here. We'll give some highlights of it. I can't go over all of it in the short time we have. But first, what we actually observed. So these were the temperature anomalies we observed over East Antarctica. On the image on the right, we have the area that is gridded, represents everywhere that exceeded the March maximum temperature value. So that gridded area, though, is the size of India, essentially. So everywhere that all those locations beat their previous March temperature record, according to atmospheric reanalysis. Station observations are a little sparse in the region. But one station at Dome C, Antarctica, did capture the magnitude of the heat wave. And if you think back to that first line graph I showed you in Canada, this is even crazier. So this heat wave happened actually during the winter transition period. So the absolute temperature values were not, well, could have been much worse, but still we had a temperature recorded at Dome C of minus 9.4 degrees Celsius, which was now the highest temperature ever recorded at Dome C, exceeding the values you would even expect in the summer, which is wild, actually. The people at Concordia Station were relatively pleased, though, with the warm weather. They definitely made the most of it. So actually, what caused the event? Well, I'll give you kind of a brief overview of the meteorology behind the event. If it, I frozen? Oh, wait, it just jumped forward. Did you do that or me? No, it's stuck, actually. Can you go forward, actually?
Yeah.
Hmm. Short break, guys. Any questions, actually, up until now?
Talk about in East Antarctica, the events are, the number is increasing, but are the amounts such that it also affects their, I mean, the mass gain? And is that captured in their, circulation laws?
So wait, the question is like,
When you talk about the number increases, but in terms of the amount of snowfall that is falling in East Antarctica due to the atmospheric rivers.
yeah,
And how far does that affect, I mean, it's a mass gain,
yeah,
is that captured by the models?
it is actually, yeah. So we are seeing like the previous image is showing, yeah, the numbers increasing and also the magnitude of snowfall increases, and that magnitude is being driven by the increasing atmospheric river frequency in that one part of Antarctica, at least. But I'm not sure. Did that answer your question?
Yeah, I'm just wondering, so if these atmospheric rivers are properly accounted for in the GCNs.
Oh, now it counted in GCMs. Yeah, that is the problem, actually. That I'm not so sure about, because that's getting to the problem of can GCMs capture extreme weather events reasonably well?
And if this could really offset some of this to a greater amount than you expect.
That is a good question. Yes, that we don't know. Is it good now? Yeah, I'm moving. Okay. Good. Oh wait, I was moving. It's a bit slow actually, but if I go back one. Okay. So back now to the East Antarctic heat wave. So going over the meteorological drivers behind this event, it was happening during a period of very active tropical cyclone activity over the Indian Ocean, in fact. So from March 6th, March 6th to like March 12th, we had two tropical cyclones in the area that interacted also with what we call a tropical temperate trough. Don't need to get into too much details about that, but basically all these various tropical cyclone activities and tropical activities kind of merge to form what we call a very large Rossby wave propagation towards East Antarctica. So essentially a very large perturbation in the polar jet stream. And we see in the images on the 16th and the 17th, now we see the mean sea level pressure increasing dramatically over East Antarctica, which was the forcing that basically caused the large, the air mass to be transported from the subtropical regions onto the interior of the East Antarctic continent. This image here now shows what we call the moisture transport, integrated moisture transport. And now you see in yellow over the southern Indian Ocean, this broad area of moisture traversing the Southern Ocean. We see here now also this first atmospheric river moving around this broad area of low pressure, beginning to move into the continent by the 15th of March. This was a relatively moderate intensity atmospheric river event. But then we see the low pressure begin to take what we call a negative tilt, and this large value of moisture transport begins to move around the low pressure system by the 16th and 17th, and then gets ejected right into the Antarctic continent on the 17th, which is when we saw the most extreme values, actually. And in fact, we looked at every atmospheric river that I could detect over the whole East Antarctica over the past 40 years. So I had 2,000 of them essentially. If I plot their average duration against the cumulative intensity of them, they normally have a linear relationship, except our event in red, which is way off the charts. And actually, it was so intense, it would be considered a destructive atmospheric river even by mid-latitude standards. So it was completely off the charts. This image kind of summarizes the meteorological background of the event. We see this large ridge, building over the continent. And we see in red the temperature anomalies moving around this blocking ridge and basically setting and lasting for several days over the interior of the continent. So implications for the Antarctic climate system, we can calculate the return time of the event, but again, we have sparse observations of the content. So this measurement is hard, this calculation is hard to make. But what was surprising is that the return time, especially the T mean anomalies over East Antarctica and Vostok, are in the matter of 100 to several hundred years, which is a lot, but not crazy actually. And so it might reflect either the extreme variability of temperature over Antarctica or the lack of our observations over Antarctica. And we try to simulate if such an event can happen more often in the future using these simulations from the IPSL in France. We see that in the blue lines, we have temperature anomalies of around 25 degrees. Those become much more common under global warming scenarios. But in red, when we have the values that we had around 40 degrees Celsius, that happens so infrequently that it's actually difficult to capture an increase in the GCMs. They show a slight increase in one simulation, but yeah, it's really hard to use GCMs to figure out their increasing frequency. But they are able to pick it up in some cases, which is encouraging. Now, the actual impacts of the event, though. So, as I said, this event happened during the winter transitional period. So temperatures were already a bit low. We still have melting around the East Antarctic coastline, which was very unusual for this time of the year. But the area was quite small. Well, actually, was the main legacy of this event was the massive amount of snowfall that it caused. Basically, the snowfall that this event created, in part with a couple other storms over Antarctica in the year 2022, helped make 2022 an actual rare positive mass balance year for the whole continent. So this event basically deposited double the amount of snowfall you would expect in March over a large part of the continent. Also, there was an ice shelf collapse that happened at the same time of this event. So we really are seeing all the facets of what I described before happening in this one event. But because this was the Conger ice shelf, it was actually a critically unstable ice shelf to begin with. So this storm kind of just kicked it out, just with the winds and the waves. So I could go into more detail about that event, but I think for the sake of time, let's keep it short. And actually, could you play that YouTube video in the background? So now, how do we examine these things further? So like my current research, I want to study more closely how these transports of poleward moisture can influence the jet stream and other heat extremes. And this video on the right is actually from a global climate model that I'm currently on this project, trying to develop the next generation of high resolution global climate models that are fully coupled with the ocean. So this isn't actually an icon model simulation that's under development. It has a global resolution of 5 kilometers. And the idea is that maybe high resolution GCMs can capture these convection processes that we don't capture today in current global climate models that might better capture the intensity of extreme weather events. And also, another thing I want to look into is that this event I showed you happened during winter and it was a net positive for snowfall. But what scares us is that what if the event happened in the summer, let's say over Drake's Glacier or another ice shelf, and created a similar anomaly? Would it represent a potential tipping point for the climate that we just haven't accounted for before. So want to see if that's actually the case. Yeah, so that's my talk. So yeah, any questions?
I spoke about previously, but the big question that I'm sure lots of people will want to discuss is, is this event and are others attributable to burning of fossil fuels and climate heating?
So these events, especially over polar regions, are hard to attribute. It's easier to attribute other events such as flooding events or heat waves because we usually use thermodynamic processes to determine how much moisture we added to the atmosphere, how much heat we added, that made the event more extreme. This event was really driven by dynamics, not by thermodynamics. And it's hard to say if the dynamics that over the Indian Ocean have changed in a measurable way that led to the creation of this event. And I think that is something we need to examine more closely in our future studies, because perhaps we are looking at a scenario where climate changes over the Indian Ocean, increased convection, could lead to more situations where events like this become more possible. So,
Yeah.
anybody else? Sure.
The previous
Yeah.
model, you in working with that model, seen any extreme events?
So yeah, my current research is to study how this model handles extreme precipitation events in the mid latitudes. And we find it is capable of actually making extreme rainfall events. Now the question is if they're realistic. This model, we only have 5 years of data so far out of the model, and the goal is to make 30 years, make one 30-year run. And even this is just going to be a prototype experiment. So we're still pretty far away from having like a stable model that is useful for the global climate community. Yep.
This is a very basic question, I think, but could it be that the increasing amount of snow falling in places where it wasn't used, or that amount trigger or produce a negative outcome in the sense of the effects that climate change we expecting in detailed time?
It's actually a decent question. So on the ice sheets, it's pretty good, but on the ice shelf and the glaciers, it's true that like we have to be careful. Sometimes you have too much snowfall. I mean, I'm not well versed in these studies, but I'm not sure if the extra pressure could, maybe I would defer to a more glacier expert, an ice shelf expert for that one. But I have seen some studies that indicate it's not always a net positive to have more snow on the ice shelves. But I don't want to give you a wrong answer, so I'm not exactly sure. Cool.
Okay, thank you, Jonathan. Our next speaker is Martin Siegert. He is a glaciologist and professor at Imperial College London, and also the co-director of the Grantham Institute. Welcome, Martin.
Thank you. Well, I was until a year ago, but all those things, I'm still a glaciologist. I'm now Vice President, University of Exeter, and I'm in charge of all the work that Exeter does in the wonderful county of Cornwall in England. So if you ever come to England, you must visit Cornwall. It's the most beautiful place. But I've been a glaciologist for over 30 years. And Jonathan, that was a brilliant talk, by the way, and that's great work that you're doing. Really fantastic.
Thank you.
I was involved in a compilation paper on Antarctic extreme events, and we referred to that event that you have been studying, and put it against some other events that have been happening around Antarctica, which we can talk a little bit about. I don't need to add to any of the things that you've mentioned, because you know far more about it, much more about it than I do. And it's brilliant that someone and a team of people are studying those things. I don't envy, by the way, not just the work you're doing, but putting together 50 different people from all around the world into a single paper. That takes some management. So well done for doing all that so well. The question, I guess, and the one that I asked is it attributable to burning fossil fuels? And it's I think the question we need to address. We might not be able to answer it, but the reason it's so important is for the reasons that you outlined, that these very high magnitude, low frequency events are really destructive in terms of what they can do to the continent, and then outwards to the world as well. So meteorological, I mean, we're talking about Antarctica, and it is largely an unexplored territory right now. I mean, we think we've got a good handle on it, but we really don't. I mean, I'm a geophysicist really, and I work on what's going on underneath the ice in Antarctica. And we've got a basic understanding of the topography underneath the ice, but that's been assembled over about 60 years from different surveys, different systems, of different techniques, different survey styles, grids, radials, you name it. And we sort of patch it all together, but it's not optimized for anything. It's not optimized for modeling. And there are many data gaps still. And so when we're talking about pretty much anything that goes on in Antarctica, I always think we are continually being surprised by stuff. And because we're learning about Antarctica, and we're learning about this unknown, amazing place. And I would place that extreme weather event, the atmospheric river, among things that we hadn't, until it happened, fully appreciated that it could happen in Antarctica. So another question is, has that happened before? And without meteorological records, I mean, there are some, and you said back to 1958, the International Geophysical Year and the Fourth International Polar Year was the establishment of meteorological stations at Vostok, for example. We've got some evidence of that going back maybe 70 or so years, but pretty much nothing before that. But we do have some anecdotal evidence, at least, and that's where delving into the history of things and talking to people that have been looking at these places much more than I have ever done, would tell you that these sort of events have never been. I mean, I started my PhD 30 years ago, and this was never considered. Melt events, even the likelihood of melt event in East Antarctica, was just never thought about. Really, not even in West Antarctica, actually, but now you've witnessed it. And so, is it just a coincidence? If it's not to do with burning fossil fuels, if that's what you're going to stick up and say, then it's just a coincidence that event happened at the same time. The level of CO2 is at 420 parts per million, and the world is 1.2 degrees warmer. Right, just a coincidence, and then they're all for nothing to worry about. It might happen in another 500 years or something, not do it. But I don't think we're in that place. I think a precautionary position is the right thing to take. And given that the need to understand this type of system more, because of the destruction that it can have on ice shelf stability, as you mentioned, on mass balance, you mentioned also, and other things, and presumably there'll be lots of sea ice melting out as well we talk about that, but presumably that would be the case as well. Those are profound impacts. Antarctica is subject to many extreme events. And again, that's not something that was in the sort of the polar scientists' lexicon. We really didn't think about it in those terms. And now we should. And I'm sure we're going to be surprised by a lot more things as more people start to study those things. I mean, you can go, when we did this little paper early this year, the reason we did it was because we were asked by essentially the UK government to understand why the Antarctic Peninsula had received so much snowfall. around about January 2023, earlier this year. And I think there was a real concern about the stability of the roofs and some of the ancient historical huts out there. They might sort of weren't capable of holding 2 feet of snow on them. And then 2023 happened, right? And warmest year on record. El Nino kicked in, but I think it's probably still too early in the El Nino phase to really have a demonstrable impact on the gross temperature of the planet, certainly in Antarctica. And yet the sea ice level in Antarctica right now, actually pretty much since June, has been at an all-time low. I mean, it's actually tracking it over time. It's quite interesting because it's not just at an all-time low. It's significantly lower than anything we've seen previously. I mean, looking at the mean compared to where we are month on month on month, it's like 2.5 million square kilometers of sea ice that should be there that isn't. And so that's 10 times the surface area of the United Kingdom. And so that's now bare ocean. And so when the sun is shining, a lot of that, of course, is much further north than 60 degrees. And so, you know, not a question of the polar winter or anything. The sun's going to be shining, and it's going to be shining on a surface that will be absorbing the radiation, not reflecting it. And preferential heating will happen. We know that's been going on in the Arctic, at least since the 1970s. The danger is it might be happening in the Antarctic as well. We haven't really, and again, up until about 2017, Antarctic sea ice, if anything, have been growing, actually at quite record levels. But since 2017, it's been retreating. Now, is that to do with burning of fossil fuels, or is that natural variability? And hand on heart, we cannot know for sure. But the suspicion is that it is, of course. I mean, because what would it take for us to be certain that it is? It will be another sort of 5 or 10 years of continued sea ice decline, like in the Arctic. But that takes us to, 2035, 2040 before we suddenly settle on the answer. Well, actually, a precautionary approach would say, actually, this is crazy. It's happening now. It's happening when the world is at 420 parts per million, 21 probably. It's happening when temperatures are 1.2 degrees warmer. It could be coincidence, but it's probably not. And so how do we resolve all these things? How do we resolve the fact that we've got this amazing river atmospheric flow causing ice shelf to break up? And I get it, it's the final phase of it. I mean, you have to prime an ice shelf, really get it ready to break up. The ice temperature has to be rising, has to have these moulins all pouring through it, surface melting, but something's got to kick it off, right? And so that can happen. The sea ice being so low. By the way, up until a few days ago, 2016, back to that year, the level of sea ice at this time of year was slightly lower than it is today. So that continual record of lowest ever sea ice hadn't broken the 2016 until a couple of days ago, and it's back. So I'm laughing because it's so ridiculous, but now it is once again the lowest sea ice on record, even breaking 2016. So what do we do about that? And we're here at COP28. I mean, there are messages that need to be spoken about and sent. And I think we need to as scientists, we have trusted voices, and we have to be very careful about the things that we say in terms of assigning likelihoods and attribution and things like that. But at the same time, even though we should be responsible about saying things, we shouldn't take that as our opinion that it isn't linked to burning of fossil fuels, and that it is a possibility, and that possibility is a really stark one, and it needs more eyes on it. And actually, from the community perspective, I think that is probably the most important issue, because when you think about how many people, Jonathan, you might be able to tell me, how many people work on atmospheric physics globally? We probably don't know, but we could probably hatch a guess that it's a lot more than study Antarctica in all its forms, actually, because I know physics departments are full of atmospheric physicists, and I know plenty, and I don't actually know in the UK that many polar scientists. And so there's a problem in that this is the most unexplored place on the planet. It's difficult and challenging to work in the polar regions, but it's really necessary that we get more people to work in them. I mean, the paper that you showed is brilliant because it's a culmination of huge amounts of knowledge and effort that allows you to do that type of work. We're just not able to do something like that in the context of Antarctica because we just haven't got the base data. We don't have the survey. The models that we have are pretty good, but they're running over bed topographies that aren't particularly realistic. And so there are so many limitations to what we're able to do, and yet we need to do it. It's important, and so we need to get better. So what's the message? We need more eyes on Antarctica. We need more people. Great that you've been involved in it. Don't leave. There's plenty more to do. And because it matters, and it matters to the continent itself, which is such a special place. But of course, as Antarctica changes, so will the world in terms of the amount of heating. Our Arctic heating 4 times the rate of the rest of the planet. Antarctica now heating at twice the rate of the rest of the planet, and with continued decline in sea ice, that's likely to continue as that polar region absorbs more heat than it would have done previously. And of course, the phenomenon on sea level rise, which we're stuck with. I mean, sea level is going to continue. It really doesn't matter what we do. We've kind of unlocked that, or the threshold's already been passed. And the question is whether we can contain it to relatively modest rates of change, or whether it actually goes much further. And just before this session, there was a demonstration on where sea level rise at 10 meters above today, where that would actually come in Dubai, and it goes straight through the conference venue at the moment. That's quite a powerful message. Now you might ask, well, when is that likely to happen? Well, that's a good question, and we really don't know. But we need an answer to that, because with unabated continued burning of fossil fuels, and the worst case scenario, 3 or 4 degrees by the end of the decade, it is possible that we stop talking about sea level rise in centimeters or tens of centimeters, and we start talking about sea level rise in terms of meters, because that's what the ice sheets, the polar ice sheets, can contribute. I mean, we know they have done that in the past. And when provoked, when the planet warms, that's what they can do. Now, whether that is in 50 years, that's very unlikely. 150 years, less likely. 300 years, it's possible. It doesn't matter, because it's decisions that we take now will determine whether it happens or not, and whether future generations are going to be able to deal with the problem that we unlock for them or not. So that's why. So my message really is Antarctica is just an amazing place. It's been, I mean, I'm speaking like it's the end of my career. I've got a bit more work still to do. Interesting. But 30 odd years in polar science has been a privilege, but it's changed a lot in that time. And I think the danger, I see it, probably likelihood, is that in another 30 years, we'll see more changes. We should expect it, and we should expect to be surprised by what happens there, unfortunately. Thank you.